Hello, this is video 66. I'm going to go over the ladder problem. It's an application of static equilibrium. So in this example, we have an 85 kilogram person stands on a lightweight ladder as shown. The fact that it's lightweight just means we can ignore the weight of the ladder. We have the floor is rough, hence it exerts both a normal force F1, that's the upward force that is shown right here. And the floor also exerts a frictional force, F2, on the ladder. The frictional force is shown going to the right here. This is because, see if you can think of it yourself before I say it, but it's because the ladder would slip to the left, so that friction force opposes that attempted motion. And then the wall is frictionless. So it only exerts a normal force pointing away from the surface, and I would draw that normal force right here to the left instead of over here. So can you think of which way would the friction force be on the wall if there had been friction? Well, the ladder would have slipped downward, so the friction force would have been upward. But in this case, we don't have any friction force. We need to find the magnitudes of F1, F2, and F3. So there are a lot of unknowns here. So let's go through our steps. The first step is to draw all of the forces. They have already been drawn for us on this diagram, but I'll go ahead and draw them again just because I don't like to use the original picture and all the extra stuff that is on it. We only want to draw the ladder, that's the object being rotated, and the forces acting on the ladder. So we don't want to draw the person. We just want to draw the force due to the person. So I'm going to go ahead and do that over here. We have the ladder. And I do like to draw the surface, but just to help me, we have a normal force over here. That was F1. We have a friction force to the right. And then we have a normal force to the left, F3. Then we have a force due to the weight of that person. That force is pulling down on the ladder. I'll call it F4. And then we are also given, you can see, what seems to be some random distances here. We have the distance from the floor to where F3 is, that's 3.8, and from the pivot point to where this weight is 0.7. So we have this force right here, and let's see, we have 3.8 from here to here, and then we have 0.7 from here to here. And I said the pivot point was right here. I didn't mean to say that because our next step is to determine where to pick the pivot point. So we will pick it here at the bottom left corner here, simply because there are two unknown forces here, and it's most of the time that's where you're going to pick it, is where there are the most unknown forces. As I mentioned in a previous video, sometimes you're going to pick it at a location where you don't care about a certain force. But in this case, we care about F1, F2, and F3, and since we don't know F1 and F2, we'll pick it right here. So the next step is to go ahead and identify all of our givens, our forces, and our distances. We are given the mass of the person who's standing here, and his mass is 85 kilograms. That was given above. So we know that F4 is equal to the weight of that person. That's how much force that he exerts on the ladder. So it's mg, or 85 times 9.8, which is going to be 833 newtons. So we know F4. We don't know any of the other forces. We don't even know the angle here. Now we could potentially solve for the angle if we knew the length of the ladder. Let's see if we are given the length of the ladder. And we're actually not even given the length of the ladder. So the reason that we're not given the angle is because we don't need it. So we don't need to spend time trying to find this angle. What we need to figure out is which definition of torque that we're going to use to solve our problem. And I give you a hint that if the object is diagonal, then most often you will use torque equals Fd. So can you see why the problem actually gave us these distances, 3.8 and 0.7 meters? Did you say that it's because those are the distances d, the lever arms, also called as moment arms? Let's take a look. If we extend, let's say, force F4 here, we extend that force, we said that the definition of d is the shortest distance from the pivot to that force line. Can you see that the shortest distance is from here to here, which is the 0.7? So that means that this would be d4, the moment arm for force 4. We can go ahead and write it here. And then let's look at the 3.8 here. Can you see that if you extend this force line, F3, and you find the shortest distance from the pivot to that force line, can you see that this vertical distance here, which is that 3.8, that vertical distance, is the same exact distance? So that would be D3, would be the 3.8 meters. So that's why it gave us what seemed to be some random distances, so that we can use this definition of torque, and it makes it a lot easier. So that's about all that we have. Let's go ahead and set up the sum of the torques equal to 0. So when we're at the pivot points, these forces, F1 and F2, do not exert any torque. But if we want it to be complete, to set up this equation for the sum of the torques equal to 0, we could say torque 1 plus torque 2 plus torque 3 plus torque 4 equals 0. And the sum of all the possible torques equals 0. And then you realize, okay, well, R is 0 for F1 and F2. They don't exert any torque. They're at the pivot points. So we can cross them out. And now we can write down what we know for the definition of torque 3. Since we're using the FD definition, it would be F3D3. And we have to pay attention, is this a clockwise or counterclockwise torque? Well, if we fix the pivot point here and we pull to the left here, can you see that it's going to rotate counterclockwise? So that's a positive torque. Now F4 is going to exert a clockwise torque. If you fix the pivot point and you pull down, you can see this whole object would rotate clockwise, which is a negative torque. So we're going to subtract the torque 4. It's negative F4D4. The sum of all those torques, where this one was negative, is equal to 0. And now we can solve for our unknown, which is F3. So we're going to add F4D4 to the other side, and then we're going to divide by D3. So we're going to plug in 833 times 0.7 and divide by 3.8. We're going to get 153 newtons. So that's F3 over here. Now we still need to find F1 and F2. So you're probably thinking, well, I don't want to do all of this again. This was a lot of work. And it turns out you're lucky. We don't have to go through all of this. Again, in the problems that I give you, we're only going to have to use this condition of the sum of the torques equal to 0. We're only going to need to use it once. That has given us enough information that we can now use the other condition, which is the sum of the forces equal to 0. So let's take a look at that one. Let's look at the forces in the x direction in our diagram here. The x direction, we have F2 going to the right and F3 going to the left. Those are our only forces in the x direction. So we can sum them up equal to 0. The sum of the forces in the x equals 0. F2 was to the right, it's positive. F3 was to the left, it's negative. What is this showing us? This is showing us that F2 is equal to F3. So you see it's a lot easier now. We just solved for F3, so we know that F2 is also 153 newtons. The same thing happens when we look at the forces in the y direction and set them equal to 0 because we're in equilibrium. If we go back up here, we can see that in the y direction we have F1 going up and F4 going down. Those are the only forces in the y direction. They must balance. So yes, that does tell us that F1 must be equal to F4. But if we are complete, we have F1 going up is positive and F4 going down is negative. So we sum them up equal to 0. That shows us that F1 equals F4. F4 was the weight of the person here, was 833 newtons going down. That means that we must have 833 newtons going up as well. So just like that, we have found our 3 unknown forces. We'll do another example in the next video. For now, just keep in mind that you really want to go through all the steps. Most of the time, you'll just have to use the sum of the torques equal to 0 after you have picked your pivot points. But if you still have some unknowns, don't forget about the additional conditions that the force can also equal to 0.